Hello everyone, I am Krish Yadav from iBot Club IIT Madras, and this is the second video of our series AIXRobotics. Our today's topic is robot task planning and the era of large language models. So let's dive right in. In the last video, we explored about robotic control, from classical PID loops to modern learning-based systems like reinforcement learning. We focused on how robots execute actions. But today, we zoom out to a layer above, that is the planning layer, where the robot figures out what it should do and how to break down a goal into actionable steps. This is the domain of planning, the layer between perception and control. In robotics, planning comes in two broad forms. The first one is task planning, and the second is motion planning. Task planning focuses on what to do, generating a sequence of high level actions to complete a goal, while motion planning focuses on how to do something, like computing a trajectory or joint angle. Let's focus on task planning, the symbolic, logical reasoning that decides what actions to take in and what order. This is where classical AI began, with planners like STRIPS and modeling languages like PDDL. In STRIPS, each world state is defined by a set of logical facts called predicates. Actions are defined with preconditions that must be true before the action, and effects that describe what changes after the action. Let's see a simple strips planning example. Stacking three blocks in order using the symbolic logic. Our goal is to reach a state where A is on B and B is on C. We start with all the blocks on the table. The world is fully defined using symbolic predicates. We apply the first action where B moves on to C. Strips verifies the preconditions, then updates the symbolic state. The world has now changed. We can see that now B is on C and the table space is freed. Next, we place A on B, finally building our desired stack. Our goal is finally achieved. Strips-based planners have found a valid action sequence that transforms the initial state into the goal state using logic. This is the core of classical symbolic planning. Using logical predicates and action rules, strips can compute a valid plan that takes a robot from an initial state to the goal. Each action is grounded in logic, and the state updates are explicit and explainable. But you might be wondering, how do we actually describe all of this in code? How do we write the actions, goals, and the state for a real planner to use? That's where PDDL, the planning domain definition language, comes in. It gives us a very formal way to implement strip style planning problems in practice. On the left, we see our final desired configuration. That is, the block A is placed on block B and the block B is placed on block C. This is the goal state. On the right is the domain file, which defines the rules of this world. The predicates like on, clear, and on table, and the move action that changes the world. The problem file defines the objects in the world. The initial state, that is, with all the blocks on the table, and the goal state, that is, the block A on block B and block B on block C. But this all depends on having a perfectly defined model of the world. What happens when the world is messy or the goal is just, can you help me make a tea? That's where learning based and LLM powered planning enters the scene. In classical planning, everything had to be defined upfront: the states, the actions, and how they change the world. But what if the world isn't fully known? What if the robot needs to adapt to new environments or learn from experience? This eventually led to learning based methods. But first, let us clarify something important. There are two kinds of planning in robotics: task planning, which decides what to do, and motion planning, which figures out how to do something. One early approach is the imitation learning, where the robot watches expert demonstrations and then tries to mimic the behavior. Another one is the reinforcement learning, where the robot learns by trial and error, receiving rewards for actions that bring it closer to the goal. For task planning, learning based methods evolved into two main directions. First one is the embedded based planning. Here, the user instructions are converted into learned vector representations. The model then maps those vectors to plans or actions. The second one is the LLM based planning. Modern approaches go further, using large language models like GPT to directly generate step by step plans from natural language. Symbolic planners were rule bound. Motion learners were low level. But LLMs, they combine high level reasoning with flexible real world knowledge. They understand language, reason about goals, and can plan across tasks without needing retraining. Large language models, or LLMs, have recently opened a new era in robotic planning. Unlike classical planners that requires hand-coded rules or learning-based models that require several thousands of training episodes, LLMs offer something very fundamentally different. They have been pre-trained on massive internet-scale data, giving them a broad understanding of the world, objects, actions, goals, and how they relate. This means that they already know what a basket is or what it means to put the towel in the basket without ever seeing a robot actually do it. What makes them truly powerful is their generalization. They don't need to learn plans during training. Instead, they can perform zero shot or few shot reasoning using in context examples just by prompting. With the right instructions, they can generate step by step action plans, infer goals, and even reason through complex tasks, all without additional training. This flexibility makes them incredibly useful in the real world robotics, where every environment and task can be different. In short, LLMs bring general purpose world knowledge, in context reasoning, and flexible planning, all at inference time. LLMs don't just hallucinate. In robotics, they are often paired with affordance models, visual inputs, or code execution to make sure the plan is both reasonable and physically possible. Let's look at the three of the most exciting systems using LLMs to guide the real robot behavior. First up is the Google SayCan, where an LLM proposes possible actions and the robot's affordance model decides what it can actually do. The name SayCan come from two different components: what the LLM says that the robot should do and what the robot can really do. The user gives a high level instruction. Let's say, I spilled juice. Can you help? The LLM ranks possible next actions based on relevance to the task. The affordant model then assigns feasibility scores using the robot's current sensors and learned skill library. SayCan multiplies these two. How relevant is this action and how doable is it? The highest scoring actions are then selected as the real plan. The LLM is typically a frozen large model like GPT-3, which provides general world knowledge and language understanding. The affordance model is trained separately using the reinforcement learning. It evaluates the Q values of candidate skills in the context. This allows the system to generalize across instructions without needing to retrain the robot for every new task. This is powerful because the robot doesn't need to be retrained for every new goal. The LLM brings common sense and world knowledge, while the affordance model keeps it grounded in physical capability. It's a clean fusion of symbolic reasoning and embodied feasibility. And that's what makes SayCan generalize across household tasks, few short prompts, and novel goals. Let's now walk through what SayCan does when it receives a high level goal like this. The LLM proposes actions that make sense based on the user's request. These are ranked by how semantically relevant they are. The affordance model checks what the robot can actually do right now based on its sensors, skills, and the state of the environment. Multiplying both the scores gives us a combined ranking. It lets us identify actions that are both meaningful and doable at the same time. This becomes the final plan that SayCan follows. The robot cleans the juice but skips throwing the towel away because the action isn't currently feasible.
Here are a few example runs of the proposed method. We start with a user instruction that says, I spilled my Coke on the table. How would you throw it away and bring me something to clean it up? The robot considers different skills that are available to it and selects the best one according to the SayCan process described above. It uses the affordance model as well as the language model to score the available options. The algorithm starts by finding a Coke can, which is then followed by picking up the Coke can. Once the robot accomplishes that part of the instruction, the skill is appended to the prompt, and the method continues with the next set of skills. On the right, you can see different skills being considered and their scores by the language model, the affordance model, and the combination of the two. Each skill, once it's chosen and executed, gets appended to the prompt, which then allows the model to generate the next part of the solution. In this case, the robot ends by finding a sponge, picking it up, and then in the seventh step of this extended plan, it brings it to the table and puts it down. Since the robot doesn't have the wipe table skill in its repertoire, it finishes the task at this point with a termination.
SayCan is a clean pipeline that lets robots plan with common sense and act with precision. It's one of the earliest and most effective LLM robot integration methods, blending reasoning with embodiment. SayCan gave us a very powerful way to combine language understanding with feasibility, but it still plans all at once in a single pass. What happens when the world changes mid task or when the robot needs to reason step by step, observing and adapting as it goes? That's where inner monologue comes in. A system where the robot just doesn't act, it thinks out loud. Like SayCan, which plans everything up front, inner monologue just thinks out loud as it moves. At each step, it prompts the LLM with a description of the current goal, the environment, and the previous reasoning. The LLM then generates the next action, and this continues in a loop. The core idea is to use the LLM as a thought engine, not just a one time planner. It mimics how humans self talk through complex tasks. The planner gets uploaded observations, which are then fed into the next prompt as a natural language. This gives it the ability to dynamically adjust. This monologue based loop gives the robot flexibility and resilience. It can recover from its mistakes, deal with partial failures, and adapt on the fly. And since all the reasoning is surfaced as the language, it's interpretable. You can literally read the robot's thought process. Here, the robot reasons step by step, exactly like our inner monologue pipeline. At each step, the model thinks, I see the fridge is closed, scanning the beer bottle, etc. Acts and proceeds. With inner monologue, the robot thinks out loud and adapts as it goes. But it's still selecting predefined skills or actions. What if the robot could go a step further and actually write its own control code? That's the idea behind code as policies, where an LLM takes your goal and directly outputs Python code the robot can execute. Code as policies is one of the most direct and powerful integrations of LLM into robotics. Given a natural language instruction like pick up the red cube, the language model generates real robot control code that can be executed immediately. Let's say the user says pick up the red cube. The LLM returns a code like this. The robotic environment exposes a fixed API, move to, pick, open, etc. The LLM is prompted with these available functions along with task descriptions and examples. This lets it generate valid, grounded policies even for new goals it has never seen before. Unlike Symbolic or RL planners, there's no need to hand code plans or train models for specific tasks. The LLM can generalize from internet scale knowledge, using in context learning to adapt to new situations on the fly. Let's say the user gives a very simple instruction: open the drawer and pick up the cup. The robot doesn't need a custom program or a training run, it just needs an LLM. The large language model takes the prompt, uses in context learning, and generates executable Python code using the robot's API. Each line here is a grounded, valid policy based on what the robot can sense and do. First, the robot checks whether the drawer is detectable. Once confirmed, it moves to the drawer and opens it. Next, it looks for the blue cup. If it sees it, the LLM generated code tells it to approach and pick it up. We have now come a very long way from symbolic logic to real time LLM guided robots. But we are just getting started. So, the question lies, what lies ahead of us? What are the frontiers in robotic planning? And how do we build systems that truly understand, adapt, and act? The ultimate challenge in planning is generalization. We want robots that can solve new problems in new environments using new tools without being explicitly retrained every time. Symbolic planners are interpretable and precise, but brittle. RL agents can adapt but are slow to learn. LLMs are general and fluent but lack grounding. The future lies in hybrid systems, combining structure, experience, and common sense. Another big direction is simulation based imagination, or world models. These allow robots to mentally simulate actions and outcomes before actually moving. It's how humans plan to. We imagine before we act. We also need robots to collaborate better, to explain what they are doing, ask for help, or clarify ambiguous instructions. LLMs open the door to truly conversational planning, where humans and robots can plan together. Finally, the biggest hurdle isn't just the ideas, it's deployment. Planning needs to work in the real world with messy sensors, missing data, and dynamic changes. That means robust pipelines, real world validation, and open ended learning. Planning is the heart of intelligence. And with LLMs, we have taken a giant leap forward. From symbolic logic to language driven reasoning, the path ahead is really very exciting. Thanks for watching. I am Krish from iBot Club IIT Madras, and this was the AIXRobotics series episode 2. Like, share, and subscribe for more deep dives into AI and robotics.